Hi, I am McKell, and today I will be presenting my work on detecting when medical segmentation models are likely to fail. I would like to thank the funding of this project. AI models tend to struggle to generalize to information they did not see during training. An example in our lab is a liver segmentation model that performed very well on external validation, but failed on the introduction of novel information, such as a stent in A and ascites in B. So the main purpose of this project is to see if we can detect when these segmentation models are likely to fail. We want to do this so we can protect against automation bias, as these segmentation models do perform well in the vast majority of all cases. Our proposed methods are to extract the bottleneck features from a UNet architecture and then reduce the dimensionality of these features using principal component analysis. Once we have these reduced features, we can then apply the Mahalanobis distance, and images with large distances would be considered to be far from the training distribution, and thus our segmentation model will be likely to fail on these images. The benefits of our methods is that they can be applied to any trained segmentation model. Simple to implement, our code is on GitHub, and as well, it's computationally inexpensive. We apply our models to a Swin UNETR segmentation model that was trained on T1 weighted liver MRIs from 3 public data sets. We then test our segmentation model on in-house data. From this test data, once a segmentation model is trained, we split the test data into 2 categories. In distribution for the images that the segmentation model performed well on, such as a dice coefficient over 95%, and added distribution that the model did not perform well on. Additionally, we have access to T1 weighted liver MRIs that were flagged for poor image quality in the clinic due to MRI acquisition artifacts. We found that principal component analysis outperformed the other dimensionality reduction methods, resulting in high performance and a low false positive rate. Visually, we can see that even when only 2 components were used, there's a visual separation between the mapping of the in-distribution data and the out-of-distribution data, with most of the out-of-distribution data being mapped outside the first standard deviation of the training dataset distribution. We found a similar pattern for the MRIs with acquisition artifacts. As an added bonus, when we looked at our training dataset, we found a whole cluster of images that were of poor image quality. They were in fact found to be very blurry. In conclusion, our methods can be applied to any trained segmentation model to detect when the model is likely to fail on images. We found it to have high performance and to require minimal computational load. And the main purpose of this whole project is so that we can implement this with our clinical implementations of segmentation models so we can warn clinicians when these models have likely failed, thereby protecting against automation bias. Check out our GitHub and paper, and thank you so much for your time.